that we have learned how to implement that to calculate the power being stored in that element, and then the energy also stored in that elements. Then we learn now that actually when the switch is on or switch is off, we know that from the capacitance law, integral and differential form, that these elements, the circuit element, they store energy, and they do not have all the time constant of steady state voltage value or steady state current value. Yeah, in the case of the capacitance, the voltage is continuous, but the current is not continuous. In the case of inductance, the current is continuous, the voltage is not continuous. And so then we learn all those things, yeah, in the previous chapter. Now we are going to learn the transient behavior of the circuit. So whenever the circuit, actually we have a little bit touched this discussion in the end part of the previous chapter, yeah, when we discussed some of the example of the memory, the DRAM memory, and how the DRAM memory behave. So the DRAM memory is based on switching. So the logic memory is stored and then also released, yeah, the 1 and 0. So the switching plays role when the logic is being stored as charge. So here in this chapter we will learn how the circuit behave in the transient time. So in circuit with inductors and capacitor voltages and currents cannot change instantaneously, they change with time. Okay, they do not, even when you switch on the circuit, the voltage or the current does not change immediately to that particular value. It changes slowly with time, which this depends on the value of the resistor that is in series with that, or the capacitance value itself, yeah, in the case of RC circuit. So even the application or removal of constant sources creates a transient behavior. Okay. So in this chapter, we will learn first the first order circuits, hopefully by this week and also next week, the first session of next week. And then we learn the source order circuit is when the circuit only contains a single energy storing element, either it is a capacitor or inductor. Then we will also be learning about second order circuits in the third session of the next week, or the week after the next week also, if we cannot finish it by next week. In the second order circuit, the circuit contains two energy storing elements in any combination. It could be RLC, RCC, RLL, etc., etc. Okay. So the conventional analysis using mathematical model requires the determination of a set of equations that represent the circuit. So this we have already done in the previous semester in electrical circuit 1. We determine the set of equations that represent that circuit. In the case of in the electrical engineering 1, we use only resistor, yeah, the passive circuit element. So that is very simple. So we use Ohm's law, we use Kirchhoff current law, we use Kirchhoff voltage law, and then we can solve the circuit based on the equation that represent that circuit. So once the model is obtained, then the analysis requires the solution of the equation for that cases can be solved, can be done, and the analysis can be done. For example, we have learned about node analysis, we have learned about loop analysis of resistive circuits. One represents the circuit by a set of algebraic equation. Then with that set of algebraic equation, we can use substitution, we can use elimination, Gauss elimination, etc. And if the set of the algebraic equation becomes complex, we can use also programming, some coding using Octave, yeah, to solve the set of voltage or currents. For example, here we have learned how to solve this. a circuit having two independent sources. Yeah, one current source IA, the other one current source IB, and then R1, and then we have R2 here, and we have R3. So we can model this using, in this case, this is a Kirchhoff current law. Yeah? G1 plus here G1 here at this one, G1 plus G2 V1 minus G2 V2 equals to IA. This is Kirchhoff current law. Yeah? In the second node here, minus G2 V1 plus G2 G3 V2 equals to minus IB. Okay, this is when we express in the form of conductance, yeah, instead of capacitance. Sorry, inductance, conductance instead of resistance. So when there are inductors or capacitor, the models becomes linear ordinary differential equation, ODE. I believe Pak Agus or Pak Fatoni already teach you this, yeah, ordinary differential equations. I think also you have learned this also in high school. Okay, why there is linear or becomes linear ordinary equations? Because of course then we have the capacitance law and the inductance law, which is usually expressed in differential form or integral form. Then they become, if they can be simplified into linear ordinary differential equations. Hence, in general, one needs to all those tools in order to be able to analyze circuits with energy storing element. Those tools, yeah, from the differential equation. So a method based on Thevenin circuit will be developed to derive the mathematical models for any arbitrary linear circuit with one energy storing element. Okay, we will develop based on the Thevenin method. Remember Thevenin method, where we replace the whole circuit and load as a voltage source and a series in resistor. The general approach can be simplified in some special cases when the form of the solution can be known beforehand. The analysis in these cases become a simple matter of determining some parameters. Two such cases will be discussed here in detail for the cases of constant source. One that assumes the availability of the differential equation, and a second that is entirely based on elementary circuit analysis, but it is normally longer. Okay, so we will discuss this performance of electrical of linear circuit to other than better simple inputs. Okay. So this is an introduction. For example, inductors and capacitors can store energy. Under suitable conditions, this energy can be released. Yeah, so they store energy first when they are charged. Then when it is switched off, this energy stored within that capacitor or inductor will be released to the load. This is the principle that you usually use in a power bank. Yeah, when you first charge the power bank, yeah, you put into the power outlet, you store it, and then it is full. Then when you release, and you can use that stored charge within the power bank to charge your energy deficient smartphone. Okay, so basically, power bank contains capacitors. The rate at which it is released will depend on the parameters of the circuit connected to the terminals of the energy storing element. Okay. Here, for example, with the switch on the left, the capacitor receives charge from the battery. So when the switch is to the left side, here the capacitor will receive charges from the battery. Okay, so the battery will fill the charge of the capacitance. Then when it is switched to the right side, to the right hand side, okay, then this will the charge inside the capacitor will be released and filling and flowing as a current to the load here, represented by this resistor. Okay, then switch to the right, and the capacitor discharges through the lamp. Okay, so when we look here at how the characteristic of the discharge over time is like this. So when it is charged, when the capacitor is charged, then it will have the same voltage as this one. The initial voltage is V0. Yeah, then it is discharged. Yeah, this is the discharge time. Immediately discharge, and the charge will go to the load. This is the charging time when it is charged. Yeah, when it is switched on, like this, the capacitance is charged with the charges from the voltage source. So you see here, they are not instantly charged or instantly discharged. It varies with time. The voltage varies with time. So the purpose of this chapter is to understand the characteristics of this charging or discharging with time. How quick or how slow the charge is being released or being filled into the capacitors. Okay, so the general response for first order circuit, including the initial, we have to include always the initial condition. Yeah, because we are working with linear ordinary differential equation, there is some information regarding the initial condition should be given or should be known. So this includes the initial condition, the model for the capacitor voltage or the electric current will be shown here to the form of this ordinary linear differential equation, ODE. Yeah, which you have learned hopefully in calculus or in engineering mathematics later. So dx dt, dx here is the value that we want to find, either it is voltage or current later, plus a xt, a is a constant, equals to ft, ft is the forcing function. And then the initial value of that parameter x at 0 plus means from 0 second, then to the right, yeah, to is the value of x, or could be or simplified as x, just as x0. Okay, so then this can be re-expressed again as this one. So if we divide each of the term with a, with the parameter a, so this becomes tau dx dt. So it means tau here equal 1 over a. Yeah, and x t equals to fth. Yeah, the Thevenin equivalent force function. Solving the differential equation using integrating factors, one tries to convert the left-hand side, LHS means left-hand side of this equation, into an exact derivative. So from mathematics, from calculus, we know that the solution to such a differential equation is, we can try using this 1 over tau exponent t over tau. Okay, so if we put this into this equation, so the here, yeah, we multiply each term with this one, so this become because 1 over tau multiply tau becomes 1, so this becomes exponent t over tau dx dt plus this one 1 over tau exponent t over tx equals 1 over tau exponent t over tau fth. Okay, so from there, yeah, this terms, use pen now. These terms, if you know that duv, yeah, let's say for example dt equals to u dv dt, right, plus v du dt. So these terms basically will be equals to d dt exponent t over tau x. Okay, so if we differentiate this one, this will be e exponent t over tau dx dt, and then x Differential of this one will be 1 over tau exponent t over tau, right? The differential of exponent value, exponent function is also exponent. Remember this from calculus, yeah? Transcendental, the differential of transcendental function is also in calculus. Okay, so if we do integration, of both sides, then this becomes the integration of d dt exponent t over tau x will become this function, yeah, exponent t over tau x. Okay, exponent t over tau x t from t0 to t, so becomes exponent t over tau xt minus exponent t t0, yeah, because the t value, the lower limit is t0 over tau times x at t0 equals to integral of from t0 until t 1 over tau exponent x over tau fth x dx. So now we change the variable to x because we have put the t in the limit, the lower boundary and upper boundary of the integral form. Okay. Then we multiply again with exponent minus, yeah, exponent minus t over tau, yeah, each of the term. So what will happen? This become xt, yeah, exponent t over tau times exponent minus t over tau becomes exponent 0. Exponent 0 equals to 1. So this become xt. So minus here exponent t0 minus t over tau. T0 minus t over tau, or we can re-express it as exponent minus t minus t0 over tau. And in the left side, we change to the right-hand side of the equation. So this minus becomes positive here times xt0. And this value, after we multiply with exponent minus t over tau, become 1 over tau is a constant. So this can be put outside the integral symbol. So 1 plus 1 over tau, integral from t0 until t, exponent minus t plus x, minus t plus x, or we can rearrange it as minus, and then inside parenthesis t minus x over tau, and function of the fth here x dx. Okay. So this is the general expression of the solution xt of this differential equation. So when we derive the equation later from the circuit, depending on capacitance or inductance or resistor, we have to try to make the equation form into this format, yeah, the tau dx dt plus x equals to fth, and the initial value of the x at 0 is known. Then the solution will be xt equals to exponent minus t minus t0 over tau xt0 plus 1 over tau integral from t0 until t exponent minus t minus x over tau fth x dx. So this expression allows the computation of the response for any forcing function. The forcing function here is the f. Initially it was ft here, but after we rearrange the expression, we re-express the expression as in this form, it becomes fth, the forcing function. So we will concentrate in the special case for this particular section when the right-hand side is a constant, so fth is a constant, yeah, when we have a constant voltage source like that. Okay, so tau here, let me erase this first. So it doesn't look. That's you. Yeah, the tau here is the time constant. Yeah. So here, from based on this equation, we know that the value x itself is varying with time. Yeah, so similar like what we have shown in the previous slide. Yeah, here it's varying with time. The value xt here is varying with time. Xt can be voltage. It can also be current. Okay. So it is the time constants representing how fast or how quick the parameter change over time. Yeah. It will be shown to provide significant information on the reaction speed of the circuit. So this is important. For example, if you are designing a memory, like the example in the previous chapter, right? The memory has to maintain, capacitance memory has to maintain, for example, 2.4 over how many seconds, how many milliseconds. So this depends on this tau. The initial time, T0, is usually arbitrary. The general expression can be used to study sequential switching. Okay, now let's take a look on the derivation of the solution if we have first order circuit, usually a circuit containing only single energy storage element, yeah, either single capacitor or single inductor. Yeah. And now with the special case where it is connected to a constant source, yeah, either a constant current source or constant voltage source. So the basic differential equation form of such circuit will be this. Should be, we have to rewrite or re-express in this format. Tau dx dt plus x equals to fth. Okay, tau dx dt plus x equal fth. Fth will be the forcing function, which will be dependent on this constant source. Then we have the initial condition has to be given as well. So if I later in quiz or exam I didn't give that, you have to ask for the initial condition, because otherwise we cannot derive the general solution for the xt. Then if we have expressed the equation for that first order circuit in this form, then the solution will be in this form. Xt equals to exponent minus t minus t0 over tau xt0 plus 1 over tau integral t0 until t exponent minus t minus x over tau fth xt, the forcing function times xt, the integral of this one. So now if the right hand side of the equation is constant, this one is constant, right? So this fth is constant, it means this is not a function of time. Okay, so this is fthx is constant for all x from t0 until t. So then this term can be taken out from the integral notation. Then it becomes, the solution becomes, for this specific first order circuit with constant source, the solution becomes xt equals to exponent minus t0 over tau x t0 plus fth. Yeah. Now it is outside the integral form over tau integral t0 to t exponent minus t minus x over tau dx. So now we need only to do integration of this function, yeah, exponent minus t minus x over tau. Yeah, then we can simplify this exponent minus t minus x over tau into exponent minus t over tau times exponent plus x over tau. Yeah, like this. For those of you who have not understood yet how this can be like that, please review again your calculus or engineering mathematics. This is one of the characteristic of exponent function. So from here we know that basically since the variable is in x, right? This is a constant, right? This is a constant. So this can be taken out also from the integration notation. So this is taken out. So then this equation becomes xt equals to exponent minus t minus t0 over tau xt0 plus fth over tau exponent minus t over tau integral from t0 until t exponent x over tau dx. Yeah, so only this needs the integration now. So from there, then we obtain fth tau exponent minus t over tau. The integration, the integral of this is tau exponent x over tau. Yeah, tau exponent x over tau. Okay, this is also from calculus, so please refer back. I will not do too detailed derivation here. This is too mathematical, yeah. Pak Agus or Pak Fatoni should have explained to you. Otherwise, you can ask them again. So the integral of this becomes tau exponent x over tau. Then the lower limit is t0, the upper limit is t. Okay. So from here, xt equals again like xt like this, and then this term can be re-expressed again. This term inside, yeah, exponent t over tau minus exponent t0 over tau. So the tau term here will cancel with this tau in the denominator. Okay. So from here, then this can be simplified further. Xt, since this, yeah, this times this equals to 1, right? Exponent this equals to exponent minus t over tau plus t over tau, which is equal to exponent 0. Exponent 0 is 1. So this become fth, this term. Okay. And then the other term becomes this fth times exponent minus t over tau. This one, yeah, t exponent minus t0 over tau, this term. Yeah. Why we put it like this? So that it can be put into one terms with this part. It becomes xt0 minus fth multiplied to exponent minus t0 over tau. Okay, so this is the general formula for this is for t larger than or equal to t0. Yeah, if from here this can be expressed simplified, yeah, the solution to be xt equals to k1, where k1 equals to the forcing function, the new forcing function fth, yeah, the constant source, plus k2 exponent minus t0 over tau, where k2 equals to x, the initial value at t0, yeah, minus the forcing function fth. Yeah, this is the k1. This is something which is constant. It doesn't change with time. The term that changes with time is the second term, k2 multiplied to exponent minus t minus t0 over tau. Okay, for t larger than or equal to t0. Again, the tau is the time constant. Yeah, which is calculated from the parameters of the circuit elements. So any variable in the circuit is of the form yt equals to k1 plus k2 exponent minus t minus t0 over tau. Yeah, or t larger than equals to t0. So only the values of the constants k1 and k2 will change. So this, in summary, we first solve or express the equation, the differential ordinary equation of that circuit containing a single storage element, energy storage element with a constant source in this part. The solution will be this. Okay, the solution will be this one, where k1 equal to the fth, yeah, this fth, and k2 equal to the initial value minus k1 or fth. Okay. So when we draw that equation, this will look something like that. Okay, when t is equals to t0, so this becomes 0. Exponent 0 is 1. So k1 plus k2. Okay, k1 plus k2. The initial 0 is k1 plus k2. Here, evolution of the transient and interpretation of the time constant. Yeah, and here at t equals to tau, t equals to tau. Yeah, here when then it will be k2 exponent minus tau minus t0. If they say t0 is 0, it will be exponent minus 1. Okay, so or k1 plus here is this the value becomes 0.368 k2. So every tau it reduces to 0.3682 of this value, etc. etc. So that's why this exponentially reduce. It drops 0.62 of the initial value in one time constant. The tangent reaches x-axis in one time constant. Yeah, in one time constant, it reaches the x-axis here. Then with less than 2% error, transient is 0 beyond this point, beyond this 4 tau value. The smaller the time constant, when tau is smaller, when this tau is smaller, it means it will reach the steady state condition faster. When so it means it is faster. When tau is 0.5 seconds, for example, yeah, the drops is even faster, but it is 4 seconds. The slope is, what do you call it? Shallower, yeah? Not too steep. Shallower, but not too steep. Smaller the time constant, the faster the transient disappears. See? So let's say here we have an example to illustrate the physical meaning of time constant. We are charging a capacitor. When we connect these capacitors to a voltage source Vs, and in between the capacitance and the voltage source, we have a series resistor Rs. Okay. So the capacitors will be charged with the current or flowing through the capacitors is C dvc dt, from the differential form of capacitance law. Okay, the KCL at this point A, C dvc dt, and the current, the sum of all current going out from the node equals to 0, remember? So C dvc dt equals to here VA or VC, basically VA here equals to VC, VC minus VS, the source, divided by RS equals to 0. Okay. So here we multiply each terms with RS. Yeah, so this becomes RS dvc dt plus VC equals to VS. Yeah, the VS we will put to the next to the right hand side of the equation. Okay, so then it becomes the tau becomes this RTH C, RTH times C. Remember that this is the same form as the previous equation form here. Yeah. We have to make the equation in this form. Tau dx dt plus x equals to FTH, where FTH is here a constant source, either constant voltage source or constant current source later. Yeah, from here, this is the derivation based on Kirchhoff current law. Then we try to arrange into tau, tau dx dt plus x, plus x, equals to the forcing function. Plus x equals to the constant forcing function. Okay, so from here, now this part, the x is now VC. Okay, x is VC. You want to know the capacitance voltage. The tau becomes the RTH see here, yeah, the VTH here becomes the function, the forcing function, which is basically the voltage source. Okay, because this is from the Vs move to the right hand side of the equation. Okay, the tau is the RTHC, the Vs is here equals to the constant voltage source Vs, the constant, the Vc at the zero condition, yeah, the initial condition is 0 volt. Now, so the solution can be shown to be Vc, remember, equals to Vs minus Vs exponent minus t over tau. From the previous slide, let's see here. If we have this function, the solution xt, yeah, equals to k1 plus k2 exponent minus t over tau, right? This one, yeah. K1 plus k2 exponent minus t 0 over tau. K1 plus k2 exponent minus t0 over tau. Since where K1 here equals to the FTH. So in this case, K1 is equal to the V source. Okay, and the T0 is 0. K2 equals to, let's see again. Sorry, coming back and forth. K2 here, what is it? Equals to the initial value. Okay, K2 equals to the initial value of the voltage. Yeah. So then it becomes so not initial value only, K2 equals initial value minus K1. Initial value minus K1 from here, yeah. This is K2. This becomes K2. Yeah, K2. This is K1. So K2 equals to the initial value minus X0 minus K1. Okay. So from here, then the initial value is 0 and minus K1 is minus Vs. So K2 equals to minus Vs. So that is why then the solution of Vc, yeah, equals to K1, which is Vs, minus Vs, K2 minus K2, which is minus Vs here, exponent minus T minus T0. And T0 is 0, 0 second, right, over tau. But tau here equals to Rs and C here from the circuit. Okay, so this represent the transient behavior. This the voltage source here represent from the source, the constant source here. Yeah, for practical purpose, the capacitor is charged when the transient is negligible. So when this part is already very small, then we can consider that the capacitance is completely charged. So at t equals 0 here, yeah, this value becomes 1. Yeah, so the voltage at the capacitance is 0. Vs minus Vs equals to 0. When t approaches, let's say, a tau, when t equals to tau, when t equals to tau, this is exponent minus 1. Exponent minus 1 is 1 over e. Yeah, 1 over e is 0. Here 0.62 drop. So 0.62 60. So this becomes this is becomes first is become Vs. This become minus 0.632 volt, or the VCT becomes 0.238 volt. Then when this t approaches infinity, so this value becomes 0, right? This will approach to 0. So the VCT becomes Vs, or VCT becomes that value of the constant voltage source. Okay, yeah. So this is already here. It is explained here. Let me erase first this part so that it can be clearly seen. Yeah, at value tau, okay, then this constant, this value becomes 0.36. At 2 tau is 0.135. 5 tau is 0.0067. So the longer the time elapse, the longer the time elapse, so this becomes smaller and smaller. So the VCT becomes approaching to the value of the V source. With less than 1% error, the transient is negligible, yeah, after 5 time constant. So if we draw in the graph the function of the VC, the capacitance value as a function of time, and in this one, the time, the x-axis is normalized against the tau, so time over tau, and we draw the voltage, yeah, as this, the maximum value is Vs, yeah, so this becomes Vs 1 minus exponent minus t over tau. This is the curve. When your tau is small, the voltage, the capacitor will be quickly charged like this. Okay, when tau is large, this is the value. Yeah, it takes more time to charge the capacitors. Yeah, this is when you later design as power storage. Yeah, either for example, for what do you call it? For resuscitation device. Yeah, into resuscitate heart. Forgot the instrument. Yeah, usually, you know, first it has to be charged, right, with high voltage before it is put on the chest of the patient, on the chest of the patient who is in the dead heart condition, and to resuscitate the heart again. So first charging, if you want to have quicker charging time, you have to design the tau to be small, for example. If your tau is too long, then it will be taking too long time for the device, your resuscitation equipment to charge. Then your patient cannot be revived, for example. Yeah. So yeah, while even though we are now learning the basic things in the electrical circuit, what you are learning here is important in later application when you design biomedical instrumentation, for example, either for diagnostic or therapy. Okay, I think that will be all for today.